Let's start with PCA. Imagine you have a dataset with thousands of dimensions, but most of the important information is hiding in a much smaller space. PCA finds that smaller space and reduces the dimensionality of your data. Here's a simple example. Imagine measuring students' height in both centimeters and inches. You have two features, but they're basically measuring the same thing. So the data is really one-dimensional, just represented in two dimensions. PCA finds the direction where the data varies the most and projects the data onto it. Now two dimensions become one, while preserving most of the important information. So how does PCA find that direction? First, we subtract the mean and standardize the variance. Then PCA looks for the direction that captures the most variation. This leads to the covariance matrix and its eigenvectors. The eigenvector with the largest eigenvalue gives us the main direction of variation. And if we want more dimensions, we simply keep the top few principal components. A 1,000-dimensional dataset could become just 10 dimensions. That's a huge reduction. And this makes PCA useful for visualization. If your data has 50 dimensions, you can't easily visualize it. But PCA can reduce it to 2 or 3 dimensions, so you can actually see its structure. It can also reduce memory and computation by replacing thousands of features with a much smaller representation. But PCA isn't always the answer. If your goal is reducing overfitting, regularization may be a better choice. And if you don't need dimensionality reduction, you may not need PCA at all. When you do use PCA, you can choose how many components to keep by looking at the variance they preserve. For example, if your selected components retain 90% of the variance, you've kept most of the information, with far fewer dimensions. But PCA has an important limitation. It finds directions of maximum variation, not necessarily the independent sources behind the data. And that's where ICA comes in. Imagine two people talking at a crowded party, while two microphones record them. Each microphone hears both speakers, so both recordings are mixtures of the two voices. You don't have either voice separately. You only have the mixtures. ICA tries to reverse that process. Instead of finding the directions with the most variation, it looks for the independent sources hidden inside the mixtures. So the two overlapping recordings can be separated into the individual voices. And that's the key difference. PCA finds directions of maximum variation. ICA finds independent sources. So PCA helps us compress high-dimensional data, while ICA helps us separate hidden independent signals. Two different problems, two different ideas. But both are powerful tools in unsupervised learning. And understanding ICA leads us into a completely different area of machine learning, reinforcement learning. And that's exactly where we're going next.